In a series of groundbreaking experiments made in 1831, Michael Faraday demonstrated that an electric current may be induced in a circuit by changing the magnetic flux enclosed by the circuit. That discovery is made even more useful when extended to the general statement that a changing magnetic field produces an electric field. Such induced electric fields are very different from the fields produced by electric charge, and Faraday's law of induction is the key to understanding their behavior. In this video, I would be talking about Faraday's law, the integral form, and I would be explaining part by part the entire equation, how it produces induced electric current and the other factors. This video is the continuation of my video series on Maxwell's equations. I have completed all those videos with integral and differential form of Gauss's law, and this is the time that we embark our journey into Faraday's law. My name is Shaunak and you are watching this video on my channel Physics for Students. So before we go ahead and understand this equation, first it is important for all of us to know who this gentleman was, who was Michael Faraday. Michael Faraday was an English scientist who contributed to the study of electromagnetism and electrochemistry. His main discoveries include the principles underlying the electromagnetic induction, diamagnetism, and what is called electrolysis. As a chemist, Faraday discovered benzene, instigated the clatrate hydrate of chlorine, invented an early form of the Bunsen burner and the system of oxidation numbers, and popularized terminology such as anode, cathode, electron, and ion. Fortunately, ultimately, he became the foremost Fullerian professor of chemistry at the Royal Institution, which is a lifetime position. Faraday was an excellent experimentalist who conveyed his ideas in clear and simple language. His mathematical abilities, however, did not extend as far as trigonometry and was limited to simplest algebra. Maxwell took the work of Faraday and others and summarized in a set of equations which is accepted as the basis of all modern theories of electromagnetic phenomena. Albert Einstein kept a picture of Faraday on his study well alongside the pictures of Arthur Schopenhauer and James Clerk Maxwell. Physicist Ernest Rutherford said, "When we consider the magnitude and extent of his discoveries and their influence on the progress of science and history, there is an honor too great to pay in the memory of Faraday, one of the greatest scientific discoveries of all time." This is in brief the life and certain important contributions of Michael Faraday, and now let us look into what is called the Faraday's law. So the Faraday's law sometimes looks like this. Now some of the textbooks which you will read feel that this form is quite misleading or wrong because it confounds two distinct phenomena: the magnetic induction, which involves a changing magnetic field, and motional electromagnetic force, which is abbreviated as EMF. Now, in both the cases, an EMF is produced, but only magnetic induction leads to a circulating electric field in the rest frame of reference of laboratory. This means that this common version which you see right now on your screen of Faraday's law is very much correct, only with the caveat that the E represents the electric field in the rest frame of reference and dl, which means the path of integration. Now, a version of Faraday's law that separates these two effects, I mean to say the magnetic induction, electromotive force, is something called as this, which is the flux rule, and this one. Now, this is the alternative form of Faraday's law. Now, note that in the Faraday's, this second version of the law, the time derivative operates only on magnetic field rather than on the magnetic flux, and both E and B are measured in terms of the reference frame where you are doing the experiment. Now, let us not confused between what is an EMF or how it is related to electric field. I will be explaining in the next part of the video. There are also examples how to use the flux rule and Faraday's law to solve problem involving induction, and we will cover up that also. So after looking into this equation, I would like to tell you what the Faraday's law is in simple terms. So Faraday's law of induction is a basic law of electromagnetism, predicting how a magnetic field will interact with an electric circuit to produce a electromagnetic force or EMF, a phenomenon known as electromagnetic induction. It is a fundamental principle of transformers, inductors, and many types of electric motors, generators, and solenoids. So this is basically what we call any changing in the magnetic environment of a coil or a wire will cause a voltage in the induced coil. No matter how the change is produced, the voltage will be generated, and the change will be by changing the magnetic field strength, moving a magnet towards or away from the coil. So in simple language, this is what the equation that we just saw. You can take a note on that, and that is why. So if I consider the Faraday's law in simple language, then the Maxwell-Faraday equation describes that a spatially varying, or I would say also describing time-varying electric field always accompanies a time-varying magnetic field, while Faraday's law says there is an electromotive force defined as electromagnetic work done on a unique charge when it is traveling around a conductive loop. On the conductive loop, in the magnetic flux to their surface enclosed by a loop varies in time. So I would like to demonstrate this with a very simple example. So this is a bar magnet and this is a galvanometer. Everything is at rest. So the galvanometer registers nothing. And here you see the motion of the magnet is moving on the right direction. The galvanometer also moves in the right direction. This is again at rest. So this registers no movement. And here again it moves in the left direction and it moves in the left direction. So this is just to show you that in Faraday's law, in simple language, an electric field which is induced along the boundary of that surface and a conductive material is present along that boundary, the induced electric field provides an electromagnetic force. Okay, so we come to the next part, that is the integral form of Faraday's law, where we are going to dissect the equation and look into it part by part. So the first part is the standard form, and it looks something like this. So let us look into the components. This actually shows the sum of contributions from each portion of the closed path. This C shows that it is a line integral. Remember, it is not a volume integral. This is the electric field, and this arrow obviously shows it is a vector field. The dot product is actually to find the part of E which is parallel to DL. The negative sign shows it is induced electromagnetic force or EMF opposes the change in flux, which is called the Lenz's law. We will soon look into it. D upon dt, dt is the rate of change in time, and this entire part is called the magnetic flux. So any surface bounded by C, which we will explore later part, which is called the Lenz's law. Now we come to the alternative form. The alternative form looks like this. So more or less it is the same. Sum of the contributions, this is the line integral, this is the electric field, this is electric field vector, this is the dot product. The negative sign shows that it opposes the change in flux. This is the rate of change of magnetic field, and this entire part is something which shows that the flux of the time rate of change in the magnetic field. Now one thing is important, that Faraday's law and the flux rule can be used to solve a lot of problems involving change of magnetic flux and induced electric fields. Now in particular, there are two types of problem. One is given information about the changing magnetic flux, and given the induced EMF on a specified path, determine the rate of change of the magnetic field, magnitude or direction of the area. In situations of higher symmetry, in addition to finding the induced EMF, it is also impossible to find the induced electric field when the rate of change of the magnetic field is being known. So these completes the integral part of Faraday's law. Now you will see that if I take the standard form, and this is the standard form, the induced electric field, what we call that is, it is induced at each segment of DL of the path C measured, is the reference frame of where the experiment is being performed. If I take the alternative form, which looks like this represents the electric field in the laboratory frames of reference where P is being measured. Right. So this is the induced, on the standard form we get the induced electric field at each segment. On the alternative form, it represents the electric field in the frame of reference where the magnetic field B is measured. These are two differences, or I would say important notes that we should find. Okay, we are talking a lot about induced electric field, etc. So let us find out quickly what is an induced electric field. So an induced or I would say inductive induction means producing or transferring something without direct contact, without any physical body. So this is the meaning of induced. So you can see here the lines of flux in this figure, and this is the induced. So this is the north and south pole, and I got a rotating shaft, right? So in case of induced current 2, a current is produced into your body without being into direct contact of the current carrying conductor. So this is important, written in red, without being in direct contact with the current carrying. So induced current is generally produced when current in a conductor changes. So if you take a magnet and you start moving to and fro from the conductor, you will be able to produce induced current. So this is just to let you know that what is actually induced electric field and what does it mean. So from here we look into a very daily application, what is called induction cooking, or what is an induction oven. It follows from the same principle actually. So induction cooking heats a cooking vessel by electric induction induced by thermal conduction from a flame. And what is electric induction? Electromagnetic or magnetic induction is the production of electromagnetic force across an electric conductor or in a changing field. So induction is basically a shortened way of saying electromagnetic induction. So in induction cooking, what happens is that there is an electrical induction. Electrical induction means it is the production of an EMF across an electrical conductor, and induction is basically a short way of saying electromagnetic induction. So the principle of Faraday, more or less, without touching a body or without involving a body, is something which induction cooking also uses. So here is a nice illustration. You see that is a conductive utensil, and this is the power coil, right? And there is an electromagnet once the electric power supply comes in. So induction cooking uses electric currents to directly heat your food through magnetic induction, and here it is. So you can see on the right hand side that there is the electromagnetic field and there is an electric coil. We will soon see step by step that how the cooking actually takes place. I just thought to give this example because it's a nice way to demonstrate induced electric field in a daily application. Okay, so here you see that basically induction is a shortened way, as we have seen electromagnetic induction. In a nutshell, induction means generating electricity using magnetism. As simple. It stems from the simple fact that electricity and magnetism are not separate. They are unconnected things, but two different aspects of the same underlying phenomena, electromagnetism. Now, induction cooking, sometimes in Europe it is called hop, okay, is simply an electromagnet. You can cook with it. Inside the glass cooktop, there is an electronically controlled coil of metal. So here, when you turn on the power, you make a current flow through the coil, and it produces a magnetic field and directly above it. Next, a simple direct electric current, which is flowing in the same direction, produces a constant magnetic field, right? One of the laws of electromagnetism is that fluctuating magnetism is produced only by constantly changing electric current. So you have to use an alternating current that keeps reversing to and fro to make a fluctuating magnetic field that will indirectly produce heat. And that is all that you need to know about induction cooking, right? So it generates a constantly changing magnetic field. It does not generate heat directly. You can put your hand on the top and you won't feel anything, but my request would be not to put your hand on the top. So here are the steps. The current flow, it produces a magnetic field. Direct electric current, because it produces a constant magnetic field, we use alternating current to produce a fluctuating magnetic field, and it generates a constantly changing magnetic field. So this is the use of induction or induction cooking or whatever. It is using electromagnetic induction in a sense that it actually generates electricity using magnetism, not by touching the entire thing. So this is what is called induced electric field. So that's all for today's video. This is the first step for Faraday's law, just to let you know overall the equation, its components and induced electric field. In the next video, we would be going step by step more. We will understand what is induced electric field more, then the line integral, the path integral of a vector field, and further as the equation consists of different other components. Thank you for watching this video. I hope you like this. Please do let me know your comment in the comment section, and please do subscribe to my channel. Click on the bell icon to get all the notification of physics for students. I will be back very soon with these next video where I would be explaining Faraday's law and its components part by part. Till then, goodbye and have a nice day ahead.
Thank you for watching this video. We appreciate your time and patience. If you want to connect with us and provide further feedback, comment or suggestions, please email us at contact.physicsforstudents@gmail.com. You can also follow us on Facebook, Instagram and LinkedIn. See you soon in the next video.